Hello everyone, my name is DongHeun Han and I'm a PhD candidate at the IIIXL Lab. Today I'm excited to introduce a paper titled ArtiGrasp by Zhang, Christian and others. This paper was presented at the 3DV 2024 conference as a spotlight presentation. The main idea of this paper is about manipulating articulated objects using both hands. You can think of it like a robotics task on the virtual world because it focuses on physical interaction. In the paper, two hands and the object are simulated using a physics engine, which allows them to interact in a realistic physical manner. The authors use reinforcement learning to train the hand agent in this environment, since physics engine typically treated as a black box. The authors defined the task in two main steps. First, the hands perform a basic grasp to move and rotate the object into a target pose. Second, they rotate the axis of the articulated object to reach the target angle. There are several challenges in this two-step process. The left and right-handed agent need to cooperate to complete the task step by step. However, early in the training process, the two hands can interfere with each other, ruining each other's learning progress. Since the agent make many mistakes during trial and error learning, it's tough for them to understand what went wrong. They don't have any insight into what the other hand is doing, making it difficult to identify the problem in the situation. This paper aims to address that problem. Now I will explain how they overcame this challenge. The definition of the task is this. Using two hands to manipulate an articulated object and move it to a target state in a physically accurate way. Since it's running on the physics simulation engine, the agent needs to learn what actions to take at every time step. The input is the current state of the environment, and the output is the appropriate action the hand should take. The input state includes information about the hand, the object, and the goal. The appropriate output is the torque applied to the joint of the fingers. This torque is sent to a PD controller, which physically moves the finger joint and wrist in the simulation. This process is repeated every time step, so the hands move in real time based on the agent decisions. And the goal is to train the network to make the right moves to achieve our target task. It's important to understand the input structure because it determines how the agent understands the situation. Hand features include we have three input features. First one is hand features. Hand feature includes wrist, finger, and contact force information. They are typical for hand or humanoid agent. These features allow the agent to assess its current skeletal structure. Object feature includes objects, pose, and mass. Also, the current articulation angle and the relationship between the object articulation axis and the wrist are also provided. This helps the agent understand the spatial relationship between the wrist and the axis. Finally, the goal feature provides the agent very clear instruction on what to do. The authors chose to give the agent very explicit instructions, such as the desired hand pose and contact flag to make a stable grasp pose. These clear instructions work well when combined with the reward function as follows, making the task easier for the agent. So you can check the reference data over here, and the object features. The mass is mass have the object is consists of two parts because it can be articulated. So the two mass of the object provide to the model. Now I will explain the reward function. I will explain it conceptually, not using the equations. Since the reward functions are usually very specific to the task, so it is enough to understand only the main concept. There are two main reward components. One is imitating the given reference data, which is imitation reward. The other one is manipulating the object to the target pose. It is task reward. First, for the imitation reward term, the reference poses for the wrist and the finger joint are used to calculate the reward. As I mentioned earlier, the goal input gives clues about the reference poses. Like this, it provides the difference of between the target pose and current pose. So the agent tries to minimize the difference between its current state and the reference. This real design is very straightforward and easy to learn since the agent doesn't need to overthink. The agent just follows very clear instructions provided by the goal input. This makes it easier for the agent to achieve a stable grasp pose, but also means that the agent relies on very specific instructions. To apply this to more general situations, I think it's better not to provide the goal input in such a very straightforward way. But that I think it would make the task more complex and harder, of course. So in this case, I think the authors determined to set up a very easy task to learn. I mentioned that training both hands together from the beginning made the training process more difficult. So the simple solution of it is to train each hand separately in different environments at the beginning. Then, after each hand learned independently, they were brought together to cooperate in the same environment. So this can be divided into two stages. And this kind of stage-based training method is called curriculum learning. The authors split the training into two stages. Like at the first stage, they fixed the object movement like a kinematic object, and had each hand learn separately at the independent environment. This allowed each hand to learn stable grasp pose because object doesn't move, and there's no interrupt for each hands. And after the first stage training, in the second stage, they allowed the object to move freely and had both hands turned together in the same environment. Since each hand had already learned how to make a stable grasp pose in the first stage, they were now able to cooperate without disrupting each other's training not too much. This curriculum learning approach is useful for complex problems or problems that can be broken down into smaller steps. like this. So the results. Since there hasn't been much focus on learning articulation tasks in previous work, the authors compared their method to a previous paper called DGrasp. DGrasp is only focused on grasping without articulation, and it seems like it's the author's previous work. Since DGraph doesn't use curriculum learning and its input structure is much simpler than this ArtiGrasp, so it performs worse than ArtiGrasp as expected. While I think while the authors report that ArtiGrasp outperforms DGraph in terms of quantitative evaluation, I think the numbers show that the average success rate is only about 50%, and the average articulation angle error is around 23 degrees. So I think it's not that good result for this kind of strict explicit instructions. I think although this is ArtiGraph is better than the DGraph, I think it's not a particularly impressive result in absolute terms because ArtiGraph use very clear instructions as I mentioned, as I mentioned, and was trained on a limited set of object categories. So to summarize the limitations, the model was trained on only a few object categories, which means it wasn't evaluated on generalized performance. And it requires very specific information about the object, such as object pose, mass, and articulation axis. So if there are many objects in the situation, we can choose which object to interact. And finally, it's very this kind of input structure is very far from being a user controllable interface. It requires reference data and specific goal settings and detailed object information, which means that users this kind of things that users wouldn't be able to provide in the real time. So this is end of presentation, and thank you for listening.